All right, welcome everybody. It is just now the top of the hour, and we are going to go ahead and start. So great to have you with us today. This is another one in a series of webinars we've been hosting over the last 6 months or so about Postgres topics, really intended for a lot of the audience that Redgate, specifically has come to be a part of the community, SQL Server and areas like, database areas like that, just to try and help understand the basics of Postgres. And so today we're going to talk about what we call MVCC and vacuuming. So a couple of things to get started. Again, this is me. My name is Ryan Booz. I have been with Redgate for just over a year now. I've actually been a client of Redgate dating back to, I think, 2008 or 2009. So I love the community that Redgate continues to support and encourage. And I'm just happy to be here and able to do things like this. I specifically try and help the Postgres community and Redgate in their Postgres journey. And, obviously we talk about DevOps a lot. So here are ways to contact me. I will change the Twitter icon someday. I just keep forgetting. LinkedIn, I do have a blog that is pretty active, a little quiet the last month or so, but please feel free to connect with me any way that you are comfortable with. If you need a question answered, even about the topic today, if you want to have a conversation about something, please don't hesitate to reach out. Couple of house cleaning items. Number one, this is today, we're talking about PostgreSQL, MVCC, and vacuuming. Next month, right after the US Thanksgiving holiday, we are going to come back and talk about monitoring Postgres, really the basics of what kind of metrics you can get from a Postgres database or cluster, things that you might need to really consider as you maybe even host something in the cloud, or you use a cloud hosted option like AWS or Azure and so forth. So come back and we'll talk about that and give you a little bit more information as you continue through your Postgres journey. Lastly, as far as announcements go, this session is being recorded and it will be made available. If you signed up for this webinar, you will get an email about it, and we will begin to make these available in other platforms like YouTube and so forth. So be on the lookout for that. And finally, as I go through these slides, if you have questions, please put them in the Q&A box of the platform that we're using today, and the team will feed those to me at the end. I'll let some space at the end to talk about any questions that come up. So please don't hesitate to do that. If I can't answer a question, I will be happy to do my best to find what the answer is, or a way that you could learn more about whatever that is, and we'll learn together. So please don't hesitate, and we'll do the best we can as we get to the end. All right, so here's the agenda. It is a 4-part agenda today, and this is not going to be the longest webinar we've hosted. My goal here is not to get really deep into MVCC and vacuuming. It's a really big topic, but I want to give you an understanding of how intricate and how necessary this is to the Postgres ecosystem, and how Postgres itself works under the covers, particularly when this is not the kind of concurrency transaction setup that you might be used to in something like SQL Server. So we're going to talk about what multi-version concurrency control is. We're going to talk about how Postgres is a heap database only, and tuples, and how you manage those and what that looks like in Postgres. We'll then talk about vacuuming, and finally, what vacuum automation looks like in the terms of Autovacuum. Now, for this talk, I have used, there are many, many sources that you can use to learn more about MVCC and just how Postgres is designed for concurrency and all the things that come along with that, both the official documentation and elsewhere. Bruce Momjian is one of the original team from 1996 that joined onto the Postgres open source project, has been developing Postgres for almost 30 years, international speaker, well-known in the community. And so I would say this is kind of the seminal talk about MVCC. There are lots of people that have given talks, but Bruce just kind of always has he's the guy who has been doing this for a long time. So all of his talks are Creative Commons licensed. You can actually use some of the content if you want to help someone understand more about MVCC. So some of what the content that I have is kind of sourced from his slide deck, because it's good content and it's easy to adapt for something like this. And then secondly, you'll see references to this website. This is been around for a long time. It's called the Internals of Postgres. And there are a couple of diagrams that I decided to use from this website, again, rather than just creating another version of the same thing. Just again, it felt like they were good for the explanation that I needed. And I would encourage you to go look at this website. It's a website that's provided because this gentleman loves Postgres and wants to, give more information back to the community. So please check those out. All right, let's get into multi-version concurrency control. One quick thing to note as we get into this discussion, you may have already noticed I've used the word tuple, and I will sometimes say tuple because that's where my brain is. But a tuple in Postgres, in the documentation, blog posts, and elsewhere, the word tuples is kind of foreign to a SQL Server developer. Well, what we really mean is it's an instance of a row in a database. And so the actual word tuple, or the idea around this concept of a tuple, is your database has a schema. Columns all have data types and widths and all those things. And so if you were to take like the schema and apply it to a row, a tuple is an instance of the row with that applied schema, right? I have a text field and a varchar field and an int field. And so it's really the same thing. If you see tuple in my decks, in documentation, we're really talking about rows, but it's one of those things that can be confusing sometimes if you're not used to it. So I wanted to get that out of the way because you'll see the word tuple a lot through this presentation. So multi-version concurrency control is shorthand. The abbreviation is MVCC, and it's what allows Postgres, and actually a lot of modern databases, in their own way, it's implemented differently among the databases to support highly concurrent workloads. And the goal of the workload, you'll hear this quote often, particularly in the Postgres space. MVCC allows Postgres to act in a way that readers never block writers and writers never block readers, at least in the default read committed transaction isolation level. And so is that always 100% true? Are writers never blocked? Are readers never blocked? No, it's not 100% true, but that's the design concept. And most of the time it works, and it works really well. And that's what we're going to talk about today. So that's the goal. There are tasks that will actually cause blocking at some level. Things like an index creation, if it's not done concurrently, that will cause, blocking. So something is causing blocking, but generally, as a connection is made and you insert rows, you update rows, or it doesn't matter how many, the snapshot isolation in Postgres will allow readers to just keep going, and they're not impacted by how many rows of data are changed under the covers by another transaction. So what does that really look like? Well, and again, these are the defaults for the read committed isolation level. That is what, if you don't change it, that's what you get in Postgres. There are 4 isolation levels in a relational database system that are part of the standard. Postgres actually only supports technically 3 of them. Postgres does not support dirty reads. So you cannot do a read uncommitted isolation level in Postgres. If you set it to read, it's supported. You can say set transaction type to read uncommitted, and it simply defaults. It's just an alias to read committed. And again, it's because of the implementation to MVCC, it just is kind of impossible to make it work in an efficient way. So when we're in read committed, every query, so every command that's run, will only see transactions that have been committed before it started. So the transaction ID is less than whatever transaction was assigned to my current command. At the beginning of the query, once I do something, a select, an insert, an update, whatever that is, a transaction ID is assigned to the command, transaction ID 100. And then Postgres will look at that moment to all of the other transactions that are currently in process but are not committed, right? So if I start something and there's a transaction that's still running and nothing's been committed, I shouldn't see that data in read committed isolation level. And then one little nuance here is if you do have a long-running transaction with many statements that don't commit in between each statement, that multi-statement transaction in the undercover work of Postgres will actually record the completion of its own intermediate transactions to determine if, when the next query in that transaction runs, can I see the results of the previous transaction? So that's the basics. We're looking at my transaction ID, the command transaction ID, and investigating. In read committed, everything has to essentially be committed before my ID. One thing to note here, this is unique. Again, this has tripped me up sometimes. It's actually tripped a few people that I've been working with as they need to learn Postgres or want to learn more about Postgres. The transaction ID for the command actually is not assigned. If you say begin and execute the begin statement, that does set up the transaction, but the ID itself is not assigned until a command begins to run, because there can be a lot of time between those things. Begin doesn't mean anything until some kind of command is beginning to run. That's just how Postgres does it. Other databases would actually assign the transaction ID at the begin statement. And oftentimes your tooling is doing auto commit. So every statement is its own transaction. And, so the difference between begin and running the command is really negligible, but that is just something to understand about Postgres. So if you're doing a test and you want to, start a command and open up another window and start another command, and you're doing step by step, you might notice the transaction ID doesn't increment right away. And so we'll see how that looks. So what does this look like in total? So this is the unique thing about Postgres. The MVCC implementation is done in a way that this is all stored in table on row. Most other databases that support MVCC do this in some way with an external resource. SQL Server, for instance, aside from memory optimized tables, will use TempDB for its implementation of how MVCC works in an attempt to have readers not block writers and writers not block readers. In Postgres, this all happens on the table rows. So when I insert a new row or a new tuple of data, there are actually hidden columns in every single table in Postgres called xmin and xmax, along with some other columns that are necessary. We'll see one or two of them in a minute. Xmin is the transaction ID that created this row, and xmax is the transaction ID that expired this row. So in technical terms, we call it the creation ID and the expiration ID. So xmax would, if it is populated, means the row is deleted or the row is updated. And we'll talk about what that means in just a minute. So you can select this row of data from your table, and you can select the xmin and xmax column. By default, when you say select star, these special columns are not returned, right? But they are always present for every row and every table in Postgres. Now, a delete would look like this, right? We had a value, it was inserted by transaction ID 48, and then we said delete where, I don't know what the ID, but somehow this row got deleted from my table. And the row itself, the tuple, is not actually deleted at that moment. Instead, the transaction ID that caused the deletion, that did that step, is inserted into the xmax column. And now Postgres can look at this row as it reads data to satisfy the next query and say, wait a second, if xmax is older than me or younger than me, I guess, that data is expired. I shouldn't use that data, right? It's old data now. And what we call that is a dead tuple. So again, when you delete a row in Postgres, you're not physically deleting the row on disk at that moment. You're simply marking its xmax, its expiration ID, to the transaction ID that caused that action. And then another process, which we'll talk about in a few minutes, will come along and eventually free that space up. And yes, I'll show you in just a minute that it works even if you were to update it to the same value. I'll show you that in a second. And so what this means is inserting a row gets an xmin, deleting a row in some way gets an xmax, that becomes a dead tuple. And an update in Postgres is literally always a delete and an insert. We don't update portions of a row. And again, that's because of the snapshot isolation. If my command is in process and it did have access to that first row that says hello and user data, and another process comes along and deletes it or updates it, I should still have access to the one that was in my snapshot, right? Because that was what was committed when my transaction began. And so that's why this works this way. We need to keep that row around. It's easier in their implementation to do it in the table page itself. And so if I update it from hello to hello world, I get an X max of 78 because that's the transaction ID that did the update. And I get a new row with the X min of 78, X max of 0, which means this is the current committed row. And now it says hello world. And again, that first row is still considered a dead tuple. Now, immediately, what most people ask is, well, what if I update the value to the same thing, right? I'm not creating anything different. What if I have a process that checks every so often and just updates the value and it might be the same value? Well, the reality is the exact same thing happens. So even if I simply say update user data equals hello, I'm still going to expire the previous row and create a new row with the current transaction ID. And again, it all goes back to the snapshot. Any commands in process need access to the committed data when it began. And then any processes that begin after this update need access to the newer row in which it began. So that's the difference in how Postgres works. And so again, this would be considered a dead tuple. So all of this is happening on each data page that is storing the rows for the table. And so what Postgres has to do is, as it's reading rows of data off the page to determine if it can use it, we have this concept called visibility. Now, again, there's a lot behind visibility. This is the high-level concept behind it. There's actually a thing called the visibility map and some other data that's stored when a query is run. In general, though, as Postgres reads rows from a page, it will determine if it should use it for this command using these rules. It is visible and available if the creation ID, the xmin, is already committed, it's less than my transaction ID, and it was not in process. So maybe the row has an initial ID, but it's not committed yet, right? So there is another process running that's doing something. So xmin has to be committed, and it has to be less than my current snapshot. If there is an xmax in there, then that row would be visible for my specific command if it's blank or aborted. So again, that would mean it's just inserted, nothing else has happened to it. If the expired ID is greater than mine, then that is the row that was in play, that was available when my transaction began. So along the way, another command came and updated that row, but I need the original one, right? My command still has that snapshot. And again, expired transaction ID cannot be in process when my query starts, right? So if it is, then it means that row is not available to me. Somebody's already modifying that row. I got to find the one that existed at the time that I started, before the time I started. So it might look like this. When I create rows, if my current transaction ID is 110, and Postgres actually keeps track of the newest completely committed transaction ID. And then remember I said, when my command starts, it also for my snapshot says, give me a list of all the transactions that are currently in process. They're currently open. They haven't been committed yet. When looking at created rows that have no xmax, as long as that xmin is less than my transaction ID and it's not in process. So this first table, we see 50 and 100, but they're kind of grayed out. It just means that that row is part of an open transaction that is not fully committed. Maybe I began something, I'm inserting lots and lots of rows, and then I'm going to commit at the end. Those rows should not be available until they're committed. Likewise, if Postgres is scanning rows from a table to satisfy my query, and there's an xmax on the row, then xmin and xmax, everything needs to be essentially less than my current transaction ID, and it can't be in process. And so right now, in this case, if my current transaction ID would be 110, the first row is not visible because both the xmin and the xmax are less than me. That means that it was expired before I even began. So I should not look at that row. The other two, however, have a xmin less than my transaction ID, and it's not committed yet. So it is the row that was available for my command because I don't know what's going on with it yet. As far as I can see in this transaction, that is the row that should be visible. And a lot of people talk about the transaction space, really, even in the documentation for Postgres, as a circular space. And so this is one of those concepts that's you'll hear often around Postgres and the conversation of Postgres. This is really what I've said, right? If my transaction ID is 100, any IDs higher than me are currently invisible. Any IDs lower than me, again, I'm talking about xmin, are currently visible if they still exist. And this is an integer. Both of these fields are integer fields. So they're 32-bit. They're not 64-bit fields. And so they can only store about 4 billion, give or take, values. And so what the team decided to do years and years ago is they treat the space as something circular. They take the current, the new value, they do a modulo on it with the 2 to the negative 30 to the 32nd power. And that gets us, splits the 4 billion in half. And what that means is there, for my transaction ID, there are always 2.1 billion-ish, give or take, transaction IDs that are in the past, right? So if there's a row that's less than my value in the last 2.1 billion rows, it's available to me. And then there are always 2.1 billion transaction IDs available in the future for new commands. If the transaction ID of xmin, in this case, is greater than me, it's not available. It was inserted after my snapshot began. So it's really helpful to think about this in circular space, right? This is almost like a clock. That line is turning and turning all the time with each command. Now, the question might come up, what happens when we get more than 4.1 billion rows in a table or in a database? What do we do with this transaction space? Keep that question in mind. We're going to talk about that in just a few minutes and how Postgres has solved it. So that is, before we go to the next step here, that is the basics around the data on page and how Postgres examines rows for the snapshot to implement multi-version concurrency control, which determines the rows that are available and visible to the query I'm currently running, whatever that is, select, update, whatever that might be. This is how it works. And you'll see in just a few minutes, you can literally see these values in your select queries if you want to. So now let's talk about what's really happening at the page level. All I've told you is that data is stored on a database page, an AK page, which you'll see in a second, just like SQL Server. But I haven't really talked about how it's stored. And the reality is Postgres is a heap-based database. There is no concept of a clustered index. Again, if you come from SQL Server, clustered indexes are really essential to what we've been taught of how to design our databases for the most part, right? So the data pages themselves, the data is inserted in an ordered fashion based on the clustered index. That doesn't exist in Postgres. There is a cluster command. That's a one-time action that will reorder the data in that table. But as soon as the next row is inserted or updated, that cluster's out the window, right? So just recognize that. We are always talking about pages that are simply added on to the end of the table. That's where the heap is. When I need another 8K page, the next set of data goes in that page. Now, if your data is coming in sequentially, maybe it's a time series data and it's always coming in with a new timestamp, you will kind of get natural ordering in your pages. It's not guaranteed, but this will kind of be that way so that it's less fragmented in the way that Postgres has to go use it. So this is just a good way to think about what's happening. We have a bunch of these 8 kilobyte pages that store my data, right? I could have tens of thousands of these pages for a really large database, or millions of these pages for a really, really large database. But that is where the data is stored. And as I insert rows or update rows, if there is not space elsewhere, the last page in the heap is going to get the new data. It doesn't matter if, the page, I would expect it to be on the first page because it's the letter A or the number 1. That's not how Postgres works, right? The index doesn't determine where in this set of pages it goes. So let's look at that. So, and that's really all I'm saying. We kind of add pages onto the end. If there's not space for whatever the next process is, an insert and update, then it will Postgres will create new pages, add it on to the mapping of where the index goes and where those pages are to get them off of disk when a query needs to be satisfied. And this is where all your data is. So what does the data look like on page? So this is the page itself. Now, I'm simplifying this a little bit. I mean, this diagram is good. What we're going to look at next, it's just very simplified, but every single page has a header section. That's what the blue represents. These are some of the flags. There's actually others there, but this is specific special header data that Postgres uses to understand some things about this page, one or two of which we'll talk about in just a minute. And then the next thing on the page is what we call these line pointers or item pointers. And so the item pointers are will actually refer to the location on the page where that row exists. So indexes point to the line pointers or the item pointers. And then the item pointers point to the newest version of that data. So let's say I have an index on, an integer value, and, tuple one has an ID of 1. Well, if I update something on that tuple, the ID hasn't changed, right? It's still the same ID. And so the index still points to the same line pointer. I don't have to create a new line pointer or item pointer there. And sorry, I go back and forth. I think technically in the documentation, they call them an item pointer. But there will literally be a new tuple created. The item pointer is just modified to point to the tuple, the new one. And so this kind of simplifies a lot of the work that needs to happen. Now, the problem is, and hopefully you're kind of tracking with me here, what happens if I update or delete a tuple? Well, immediately we would sometimes think, well, the data's gone, right? I said delete, the transaction completed, whether it's on this page or, I kind of put another page off to the side to say there's lots of these pages for this table. Surely it's just gone, right? I've freed up that space. Well, that's not true. That's not how Postgres works. When you say update or delete, you are marking that row. Remember, you're completing the Xmax transaction ID. That signifies to Postgres that this tuple, this row, is no longer available to new transactions. It's dead. And that's really what we call it. I said that earlier. It's called a dead tuple. And so you'll notice that I got rid of the pointers. Oops, I always do that. I got rid of the pointers from the item pointers to the dead tuples, right? That is severed right away. But the index maintenance is not necessarily severed immediately. And so what happens is we have a process, which we're going to talk about, that comes along behind the scenes, which will help free the space. But at the moment, until that process runs, if we insert new data, we're just going to keep inserting tuples, and those dead tuples have not been removed. That space is still taken on this data page. And again, we refer to that as dead tuples. And so if you are monitoring your software, your database, you will see things like the number of dead tuples in a table right now. If Postgres is not running correctly, as more updates and deletes are done, the dead tuple count just keeps growing. That takes actual space on disk. And that's why these processes exist. That and some other things we'll describe in just a few minutes. This is actually a screenshot from SQL Monitor, and you can see it's the dark blue section right here is what is kind of tracking with the dead tuple count over time. And we'll talk about when it shrinks and what's going on there in just a minute. So again, let's think about these as pages of data. And they're just stacked. Now, they're not literally sequential, right? This is just how computers work. Sometimes I'm going to create a new file. There's not space on the same part of the memory or disk, talking about old spinning disks. And so that's fragmentation, right? The next page might be somewhere else, and we have to read pages from all over the disk in some way to get this data. So here's our list of pages. And let's say we have just a basic table. I didn't fill in the data because it doesn't matter. We have some columns, but there's no index. Or maybe there's an index, but my query doesn't use that index. There's no way for Postgres to say, oh, well, I can see you want this thing. Let me go ahead and find it, right? This just says, get me all the rows. That's what this says. And what that means is Postgres has to do a sequential scan, and it literally has to scan every page. And so it literally opens every page. It's now looking, then it has to go row by row and say, all right, I'm looking at every row. And is this row dead or expired to this transaction? All right, if it is, skip over that row. This is a lot of IO. This is a lot of work. That's one of the reasons why we want to try and keep maintenance running so fewer pages and more space is available so the growth doesn't happen as much in your Postgres table. Well, let's say we do have an index. And this is the other thing you have to understand about Postgres. I have an index. I use that index in my query. You will actually find in query plans that Postgres does not always use the index. You could very likely get a sequence scan, which is the same thing as like a table scan in SQL Server, even if you use the index. And basically, Postgres says, look, because we're a heap-based database, if the table is small, I'm going to waste more energy and more processing time than is necessary trying to figure out the pages of data to go grab. I'll just grab everything. It's small enough. I'm just going to grab it all anyway, and then we'll get to it. We'll do a hash map or something. However, if the table is large, or it determines that it's more efficient to just grab individual pages, it can do that as an index scan. So recognize we're talking about pages. We've talked about these xmin and xmax rows on the page. And the goal is to keep all of this as clean as possible. So I create fewer rows. And as snapshots happen in memory or on disk, I can have less space taken for each snapshot. And hopefully the snapshots are quick. All right, so that's the basics of what a heap database looks like. Again, it goes much deeper, but this is kind of the next step. So we have the pages, we understand transaction snapshots. There's these special columns in table. They are modified over time, and as they get deleted, the rows have to be cleaned up at some point. One of the goals is to try and keep the table as small as possible. We just want fewer pages because that means less IO over time to satisfy a query. And so the process that helps us with that maintenance is called vacuuming. Generally, it is a unique term to Postgres in the relational database space. This is what they call it. And I just felt like I had to put a modern day, iRobot, Roomba, something in here just to talk about vacuuming. So what is vacuuming? Vacuuming has a number of purposes, but the two main purposes, very high level, are to free up space on the data pages used by dead tuples. So if I've deleted a lot of data from a page and they're currently dead, I literally want to make that space available for new data. And I can't do that until we have cleaned out those dead tuples. Then the other thing that, the other main purpose, there are other things, but these are the two main jobs, is to mark rows in the page as frozen. So again, when Postgres needs to satisfy a query, it's going to go find the pages that might have data to satisfy the query. Then it's going to open the page and start scanning through rows, might use an index to help with that. And then it has to look at the row and see if the row is currently available. Is the xmin older than my transaction? Is the xmax not set yet? Or is it newer than my transaction ID? It has to do all that work. Well, what if that row has been around for a year? It's never going to change. It's done. It's historical data. Well, this is where the concept of frozen rows comes in. And so what Postgres can do is say, hey, remember we have 2.1 billion transaction IDs that are newer and 2.1 that are older. Well, if the transaction ID for a row is sufficiently older than the current, transaction ID space we are making available to new transactions, and the sufficient value can be tuned, and I'm not going to get into the specifics there, but then we can say, you know what, this row is just frozen. It hasn't changed. I can reuse that transaction ID when it comes back around in that circular space. And then additionally, as Postgres has been developed, if all of the rows on a page are old enough and they haven't been changed, I can just mark the page as frozen. That is much easier to scan both the frozen page and frozen rows for all kinds of things. Satisfying a query, I don't have to examine if the transaction ID is available to my new command. If the whole page is frozen, every row on that page is just available to me. It's older than me and it's committed. If I have to scan the rows on a page, it's a lot easier to scan a bit column rather than do all this comparison between transaction IDs and free space and all this other stuff. I can say, oh, the row's frozen. That literally means it is committed and it's older. It's older than me. That row's available. Move on to the next row. So it makes scanning the data pages faster as well. So let's look at what that means for free space. So I said earlier, we have these dead tuples. The line pointer says that it's dead, but remember, we had a pointer that goes to these dead tuples, and that's been removed. However, we cannot literally free up the space until the references to those tuples are gone. So once vacuum begins, index maintenance takes place, the references to those tuples is removed, and now the vacuum process can literally remove that space, move kind of the existing tuples around if necessary. It doesn't necessarily do that. It's just easier in a visualization. And then the item pointers at the top, notice that they say unused. We don't get rid of that space. It's kind of like SQL Server saying, when you free up index space, we're not going to just reclaim all that disk because we're going to have to allocate it again at some point. So we just leave those item pointers available. And the next time a new row is inserted or a row is updated, we will use those item pointers rather than create a new one, trying to do this as efficiently as possible. And again, when this works correctly, that's when you'll see these spaces where there are a lot of dead tuples, and then they kind of went down to almost nothing. Then there's a lot of dead tuples, and it went down to almost nothing. And this is really generally a healthy database within Postgres. Oops, my apologies. There we go. So frozen rows. So that's one thing. We're freeing up space, really necessary within a Postgres implementation. And we want to make sure that that is happening so that our pages stay as efficiently maintained as possible. Freezing rows is the other thing we talked about. So the second thing that it will do, Postgres with the vacuum process, is it will say, hey, are there tuples on this page whose transaction ID is committed and sufficiently old enough that there's no chance any currently running transaction might be modifying it? If that is true, then it will mark those rows, those tuples, as frozen. That speeds up all kinds of work, as I talked about earlier. And then, like I said, it will do the same thing to the page. If it says, wait a second, every row on this page is frozen, I don't even have to look at the page. I can just mark the rows. I can look at the page as frozen. And that speeds up future vacuuming. Vacuuming says, hey, I don't even need to look at this page. That is 8 kilobyte. I don't have to deal with. If the page is frozen, that just helps move along. Now, again, a visualization is, hard sometimes. What I'm trying to show here is that, tuples continue to fill the page and nothing else has changed. And it's kind of, hopefully as efficiently used of a page as we can make. So then the last question might become, okay, we have these pages. We have a really high level concept of how MVCC is that allows us to have this non-blocking interaction between readers and writers. We now understand that we have to clean those rows up over time. Well, do I have to do that work? Is this kind of like in SQL Server where I have to run a statistics update every night and do some other maintenance? No, hopefully not. This process is so essential. It's so vital to a healthy running Postgres that years ago, the team implemented what we call Autovacuum. And so it is a process that you can turn off, but by default, it is always on in every Postgres instance and table unless you change that setting. And it is a process that is triggered by, some values, which we're going to talk about here in a second. And when that process is triggered, it will then go table by table, determining the pages of data that need to have maintenance, enacted on them in some way, cleaning up space, freezing rows, whatever that might look like. And so it's triggered on a percentage basis. Generally, if I have 100,000 rows and it's 20%, once 20,000 rows have been inserted, deleted, modified, something's happened, then this process needs to come along and make sure that the pages are, maybe frozen, data was inserted, And it was inserted long enough ago that I want to freeze those rows or freeze that page, or I need to clean up dead tuples, whatever that might look like. And then finally, individual updates and delete heavy tables can actually be tuned directly. And this is actually one of the things that I think is really cool and unique about Postgres, which you can't do in something like SQL Server or other databases. Again, because MVCC means an update, deletes, and inserts, that's a lot of potential fragmentation and dead tuples in a table page. Well, you can tune individual tables so that Autovacuum or AutoAnalyze runs more frequently to keep that table in better shape over time. If I have a table with 1 billion or 10 billion rows, 20% means I have to modify a lot of data before Autovacuum would trigger. Generally, again, there's lots of nuances in this, but that's the general nature. By default, these are the settings. Autovacuum triggers at 20% unless you modify it. AutoAnalyze, which is what updates statistics on the page, triggers at 10% modification. And this is kind of analogous to, the ability to tune this is kind of analogous to the old trace flag, I think from SQL Server 2008 or 2012, I forget when it was. Trace flag 2731 is what lowered the threshold for running a statistics update on a table. Again, as your table grows, if statistics, or in this case, vacuuming, is triggered on a percentage, then more rows have to be modified before the process runs. But in reality, you probably want it to run more frequently because you have more rows. So those are the settings. Now you can actually tune this globally as a setting of the running Postgres cluster, or you can set it per table or database, or you can set it per table. The two settings have these terms: scale factor. So whether it's Autovacuum or AutoAnalyze, the scale factor is the percentage. So what percentage of rows, tuples in this table need to be modified in some way before this process kicks in. And then the threshold is added along the way. And this is simply a static integer value that is added to that percentage calculation so that small tables don't trigger Autovacuum over and over and over again. Because if you have a lot of really small tables, when Autovacuum kicks in, it tries to go look at all those tables, and the small ones are always getting attention, and maybe resources are being taken away from the larger tables, and it doesn't complete in time. And then the next time, it's almost like Autovacuum runs behind. It doesn't catch up to itself if all these smaller tables are always getting the attention. So that's what scale factor is for. I mean, the threshold is for. So technically, if I have 100,000 rows and I'm set at 20%, by default, if I don't change anything, technically 20,050 rows have to be updated, modified before Autovacuum would kick in on that table. Last two slides, just to make sure we're on the same page. This is just such an essential process. Now that we can understand what's happening with MVCC, how it's implemented, we see how necessary the vacuuming process is. And as I said, it's a really valuable thing to know that you can modify per table some of these settings. If you have a very update heavy table, you absolutely should consider, I'm not going to say do it, but you should consider lowering that scale factor. Don't wait for millions of rows to be modified before vacuum kicks in. Lower that threshold down to 5%, 3%, whatever makes sense for your table, so that vacuuming happens more frequently. That will keep that table in shape. And same thing with the threshold. You can modify that static value. Maybe you have a bunch of tables that have static data for your application, and they're all 1,000 rows, and they get modified every so often. Well, if it's a really small number, then they're always going to be vacuumed, but they don't need to be. It's only a couple pages of data. The last thing I'll say here is, again, vacuuming is so essential that as your database grows, the memory setting maintenance work mem is what determines how much memory is available for Postgres to suck in these data pages, scan through the rows, and determine what needs to happen. Delete dead tuples, freeze rows, freeze pages. The larger a database gets, the larger table gets. If maintenance work mem is not enough, then it never is able to keep up. It is absolutely worth investigating this. There's only one maintenance work mem that is, and it does other things like building indexes. This is the memory that's used for that kind of work, really working with pages of data. If Autovacuum is running behind, you should absolutely check this setting. By default, it's 64 megabytes. And it's almost never enough for a modern database. It does not hurt to make this 128, maybe 512, because it's going to happen quickly. It doesn't mean it's going to use 512 megabyte, but if you have a really big table, it will work through that table faster if it can suck more pages in to do the work. So consider looking at this. I'm not going to give you a number. There are lots of blog posts, maybe we can talk about later, of how to start to think about this value. And again, this is what helps that space get freed up. Here's my last statement. This is attributed to somebody in the Postgres community. I don't know exactly who, it doesn't really matter. But if you think Autovacuum and Analyze is running too frequently, it's probably not. A lot of people that are new to Postgres will get something like Azure or AWS, and they see a list of queries that are running frequently, and Autovacuum is often at the top. And they think, well, shoot, I need to stop that or make it less frequent because it's stealing resources from my queries. It's actually almost never true. Again, it's a different set of memory. It's a different process than what's happening with your other queries. And if you turn it off or you back it down, you're actually going to cause Postgres to fall further behind. As a general rule, you want Autovacuum and AutoAnalyze to run as frequently as makes sense for that amount of data in that table. Those are the high-level basics. There's a lot to this. But hopefully that gets you a starting point. I pointed you to a couple of presentations. You can find videos of those presentations from Bruce and others online that will get into more of the weeds with actual queries and so forth. I was going to show you this really quickly. This is a database I have, and you'll notice that if I should have done this, if I say select star from, oops, just to show you this, when you're in Postgres, if I say select star, right, I'm going to get rid of xmin, xmax. We didn't talk about CTID because it doesn't really matter. You'll notice there is no xmin, xmax column. However, I can select them, and you can see that that data does exist. And this is, so in this case, this would be the transaction ID that created that row. You'll see that it's not deleted. And this is actually, CTID is the actual pointer to the item on page. So this is what actually allows Postgres to go find that row of data if that's the one you need. Pretty cool. All right. So one last thing to talk about is just what's coming up. If you haven't heard, Past Data Community Summit is happening in just a few weeks. I'm so thrilled about just seeing this come together again. And we actually have really a Postgres track. It's something that's available to you. We now have, I think, 13, 14, 15 Postgres sessions. Postgres US, the PGUS team is actually going to be on site. We're going to have a panel about Postgres with a number of the contributors from the community. So it's going to be really fun for me from a Postgres perspective. There are two things that you can register for. One is a full day pre-con by Ryan Lambert. It's about using PostGIS with Postgres. Really cool. If you want to understand mapping and geospatial stuff, Postgres and PostGIS is literally like the gold standard in the relational database community. Ryan is an excellent teacher. He's actually a SQL Server DBA for his career, but he loves geospatial stuff. He's been doing PostGIS for years, and he's just really knowledgeable about this. And it's going to be fun. It's going to be fun to create maps based on data and see how data changes over time, things like that. And then we do have a sponsored session, which is from AWS. A lot of people are using AWS RDS. And so we have this session called a 3-step guide to modernize SQL Server to Postgres. So how to get from SQL Server, if you want to transition over time to Postgres, a way to do that, and tools that you can use in the AWS space. I'm going to be at Summit all week. If you come, please come find me and say hi. I'll be with the Redgate team. I'll be helping with a number of sessions. And I just can't wait to see you. If you haven't gotten your ticket yet, it's not too late. You can come to any of this. So please head over to pastdatacommunitysummit.com and get your ticket. And as I said earlier, so here's a couple questions we had. Question 1. So Postgres is always auto commit. No, the tooling is always auto commit. You can begin a transaction and not commit it. Almost all tooling everywhere by default is set, whether you're using a language like Python or .NET. All of those frameworks by default that I know of, and I'm not going to speak as an authority, they just by nature, auto commit is the thing. You start the transaction, you run the thing, and you complete it, it will auto commit by default. And then most tooling, whether it's Azure Data Studio, dbeaver that I use, whatever tool you use, even pgadmin, all of them by default are set as an auto commit. So just have to look at the tool, decide how you want to do it. There's usually a way to not auto commit if that's necessary. And it is, right? If I want to process a batch of rows, I don't want to commit for every row. That's a lot of extra work that's unnecessary until the thing is done. Question 2, in a multi-statement transaction, it will or will not see the change data, a previous statement in its change made. Yes. So if a multi-statement transaction happens and the first statement updates a bunch of rows and the next statement selects, it's in that transaction, and the transaction ID, again, it's keeping track of those transactions. It will potentially, I shouldn't say yes. If it does all that comparison work, potentially it will be able to see that data. That is an artifact of if the data is committed within that. And again, part of this is in Postgres, you can actually commit in the middle of a transaction. So you could, every statement is the beginning of that transaction ID, right? So if it is committed, it could be available. I'm not going to say it always will be, but it could be. Is Autovacuum, question 3, is Autovacuum only available from Postgres 16? Oh no, Autovacuuming, great question. Autovacuuming has been available for a long time, probably Postgres 8 or 7. It is just so essential that they instituted that process a long time ago. Now, a lot of the updates over the last 10 years, things like freezing rows and pages in new and better ways, those have been improved over versions of Postgres, but Autovacuum is available in any modern Postgres that you can get access to yourself or through a cloud platform. It's absolutely there. It should be turned on by default. And again, I'd really caution you about turning off Autovacuum at the database unless you really know what you're doing, because it almost always will end up going south on you if you're not really careful. So really, really consider tuning Autovacuum, not turning it off and doing something yourself. Last question that has come through right now. Below link says, Postgres has slower performance compared to other RDBMSs like SQL Server and MySQL. What is your take on that? It's a cloud, Google Cloud link. I could point to actually something that was just published today or yesterday about, there's a gentleman in the community, actually used to work at Facebook, helped develop RocksDB, which is the MySQL variation that backs Facebook. Mark Callahan, he's been doing database benchmarking literally for years. Every new update from MySQL and SQL Server and Postgres and Oracle, he will run benchmarks to see if there's regressions. And he'd actually just posted one yesterday about how the newest version of MySQL actually has an insert regression. It gets slower over time. It's just not true. It really, modern databases are modern databases. Postgres has a lot of functionality. It all depends on your schema and design. It depends on the power of your server. It depends on the memory. Again, Postgres has 6+ index types. None of the other databases have that. And you can create your own index type, which might actually make a lot of things faster, depending on your query type. So I'm not going to get into the debate. I appreciate that Google said that. There's absolutely going to be times where SQL Server is faster than Postgres. Postgres is going to be faster than SQL Server at something else. And it's just a nature of how some things work. So you'd have that discussion. If you're at Summit, we'd happy to do that. Another question, what is the best way of vacuuming on a Redshift? How often do we need to do it? Oh, interesting question. Redshift is a different beast. I have been a Redshift user in a previous life. It's probably been 4 years since I've really done a lot with Redshift. For those of you who don't know, Redshift is Amazon's massively parallel processing data warehouse. It is forked from a very old version of Postgres, I think version 8.1, 14 or 15 years ago. And so it is Postgres by nature. There's a lot about it that is not Postgres, right? Not a modern Postgres. I'll be honest, I've never spent a lot of time on understanding how the vacuum process works, because Amazon, when they, and the company they bought that product from, they actually changed the storage layer into a columnar storage, which is what allows it to be massively parallel. I I could try and find that out. Again, if you want to reach out to me in a couple of ways I told you to earlier, I can go back to that slide in a second. Basically, Ryan Booz, RyanBooz on all social platforms. For the most part, you should be able to find me. I could look into that and see, and maybe I'll learn something about how vacuuming is working in Redshift nowadays and go from there. All right. We've come in under an hour. I hope this was helpful as just a starting concept. When you hear Postgres, you see things about Postgres and MVCC and how bad it is. Let me just share this. Sorry, this came to mind. This is softwareandbooze.com. So this is my website. I'll drag this over here so you can see it. And I was at a conference a few months ago, and actually, this is a common thing. And so I wrote this blog post after being at this conference called In Defense of MVCC and Vacuuming. So it is an easy target for a lot of other database systems to come after Postgres and say, look, there's this thing that's old and antiquated. And at the end of the day, Postgres has been around for 30 years, essentially. Actually, it's been around for 45 or 50 in various forms. But what we know as Postgres today is almost 30 years old. And this concept of MVCC and vacuuming has been around for a long time. And there are absolutely times where it can really get you in trouble if you're not careful. You'll hear about things like transaction wraparound, which will actually make it would just stop Postgres from working. If vacuuming doesn't work and a database runs out of new transaction IDs because the old ones haven't been cleaned up or frozen, you can get into a bad state. That's almost literally never a problem in modern Postgres. If it is a problem, it means that your database is not being managed correctly. That might mean you don't know how. Maybe turn off vacuum and you never understood that it needed to be turned back on. But it works pretty well in our modern space. There's been a lot of other things that the team has done to stop lots of database growth and make sure those pages are as efficient as possible. So I just encourage you to, just do some research on what you need to do and how you need to run Postgres efficiently, and just do what you can with it. So, all right. It's been a pleasure going through this. It's a hard topic. There's a lot more. Go look at Bruce's topic, reach out with questions, and just start to dig even further into what Postgres is. Thank you so much for your time today. And I really hope that you have a great rest of your week. And again, I hope to see you at Past Data Community Summit in a few weeks. Take care.